Good evening, everyone. So we will start today's section, week 3, digital VLSI testing course. So today we will discuss about the simulation part, like the logic and fault simulation. So, just a second. So the logic simulation is used to predict the behavior of a design. Like we are just simulating what is the behavior and without doing any physical realization and for verification of the design. So this is the flow chart where like once we have a specification, we write the design and then we can perform synthesis. We get the circuit. We can have a test bench which we can apply to this. We will have a simulated response which we can compare with the golden response and perform the analysis. If we have any bug, we can we can go back to the design and synthesis. Otherwise, we can go to the next stage. So this is just a basic simulation flow where we have this expected results, which is the golden results applied for the response analysis. So it predicts the behavior of a faulty circuit. So as a like logic simulation is for like just for the design and not the fault. So fault simulation we will have for the in the presence of a fault. What will be the output? So this is the complete fault-free simulation. So next, this is just an example to show where gate level circuit and the interconnection of a gate level design logic circuits. Next, if you have a sequential circuit, we will have a flip-flop. And now these are the terms like we have already seen. Primary inputs, these are the primary inputs and these are the primary outputs. And this scan flip-flop will be connected as a scan chain which will have a scan input and a scan output. This is known as pseudo primary, and the scan input and output can be known as the pseudo primary input and the pseudo primary output. So the next is the D flip flop, which is you can see it is a edge trigger, and here no bubble, so it is a positive edge trigger D flip flop, and this is just the internal circuit, gate level circuit of this D flip flop. This has the clear with the clear and preset signals. So the next is the logic symbols. So the commonly we have 0, 1, U and this V. These are the symbols used for the during the simulation. So if we consider two value logic or the two value the Boolean algebra, we consider 0 and 1. These are the two symbols where 0 means it's a false and 1 indicates it's true. And we further have a symbol with U, which is known as unknown logic. So the outputs can either be 1 or 0. And we have another symbol called Z, which represents an high impedance state. Where it is the if this is the line, it is floating without connecting to the either VDD or ground. So it's like one. So it's like not connected to VDD or ground. With this, we could have already seen if we have a binary logic, if we consider an AND gate, say 0 and 1, if both the inputs are 0, 0, output is 0. Any one input is 0, output is 0. And 0, 1 is again 0, 1, 1 is. Now, if we have a ternary logic, we will have three logic symbols. Which are 0, 1, and U. So now we have to simulate that output for the U input also. When one input is, but this is a controlling value, so output will be 0. This is a non-controlling value, so we don't know what will be the output, whether 0 or 1. And again, this is 0. Here we go. U and U will also be unknown. So in a similar way, if we have for an OR gate, 0, 1, U, 0, 0, 0, 0, 1, 1. Here for an OR gate, 1 is a controlling value. So now 0 is a non-controlling value, so unknown. 1 is a controlling value, 1 is a controlling value, and these are unknown. Similarly, for if you consider a NOT gate, so we are defining this for all the basic gates and our what will be the ternary logic. So this will be the normal binary. You will give U. So you will see that if we apply the ternary logic, so there is some information loss. So if you say simulate this, considering this as an unknown. So simulation based on ternary logic is pessimistic. So a signal may be reported as unknown when its value can be uniquely determined as 0 or 1. So you can see if we have an unknown from the previous ternary logic table, 0 is a non-controlling value. So U will be, we will obtain U here. And this is having an input U and U. For an AND gate, one is a non-controlling, again output will be U. And for U, if applied through NOT, it is U. So U NOR with U is also unknown. But if we have U is it's like 0 or 1. So if you simulate 0 or 0 is 0 or 1 or 0 is going to be 1. So we know it is 0 or 1, 0 or 1. So if we apply a NOT operation, it's going to be 1 or 0. Similarly, here this is a non-controlling value, so we will get this. So both are never going to be the same. So for an OR gate, we can say it's going to be 0. 1 or 0 or 0 nor 1 is going to be 0. So if we could have evaluated as keeping as 1, 0 or 1, we could have got that deterministic value, but because of using the ternary logic, we are getting as a U. So there is an information loss when we are using this ternary logic. So next, this high impedance, we have said that it is represented as a Z symbol. So what is this high impedance? So if we have some tri-state buffers and they are driving say some uh, to this node, which is connected to some resolution function, and based on this it is either pulled up or pulled down some operation, and which output is connected to some logic gate, either to the next combo logic or to flip flop and to some next stage. So this value, if if this potential is floating, then it's like not connected neither to VDD nor ground, then that potential that value will be like at a high impedance state. So this is a tri-state gates permit several gates to time share here through a common this common bus. So signal is high impedance state if it is connected to neither VDD nor ground. So it's called high impedance represented by Z if neither connected to VDD nor ground. So what is the bus conflicts? If that is the conflict occurs if at least two drivers drive in opposite value. So if this value is 1, this value is 0, so there is a conflict between these two buses. So to simulate a tri-state behavior, one may insert a resolution function for each bus or wire, and we have another logic called as multi-value logic to represent this intermediate logic state. Next is logic element evaluation methods. So the choice of evaluation technique depends on the considered logic symbol, type and model of the logic element, and the commonly used methods. This we will discuss briefly. So the logic evaluation methods are truth table based method, the input scanning method, input counting method, and parallel gate evaluation method. So with this, we will briefly discuss one by one. So the truth table method is like we have say 3-bit, then ranging from all 0 to all 1. This will have some output. If we have a 3-bit input I1, I2, I3, this will have some output. So evaluating this completely. This we set the truth table, which is like testing exhaustively. And so this is most straightforward and easy implementation. But for a binary, if we consider, then we will have 2 to the power n entries for n input logic element. So we can just store this output in the memory and use this index like 0th element, first element as the input. But this table size we have seen it's 2 to the power n. So it's like increases exponentially with the number of inputs. So if and this could be inefficient when we go for a multi-valued logic. So if we consider a multi-valued logic, then if we have say k symbols, k symbol logic system, so and n input logic element. So now instead of like having two symbols 0 and 1, if we have k such symbols, then the number of entries in the table will be 2 to the power m to n, where this m is log of log base to k, and this is the seal. Like we will take the maximum value. Like if we get 2.1, we will take consider as 3. So this is that operator. So table index can be now indexed by m into n. So this many entries we will have in the truth table. So this is the truth table based method and how it is growing exponentially with the n. Also, if we have multi-valued logic, then it is like 2 to the power m into n, where m is the log to k, log base to k. So the next evaluation method is the input scanning. Now, if a gate, for example, is like this, and this input is say 0, this value we call as the controlling value. So if any input has the like any input is the controlling value, then the output of the gate is given as C XOR I. I is the inversion, and otherwise, if any of the input is unknown, then the output is also unknown. Otherwise, the output of a gate is C complement, complement of the controlling value, XORed with the inversion. So the next, we give the controlling and inversion values for the basic gates. The C is the controlling and I is the inversion values. For an AND gate, controlling value is 0 and inversion is also 0, or controlling is 1, inversion is 0. For a NAND gate, it's a complementary gate, so the inversion is 1, and for NOR also, it's a complementary of OR, inversion is 1. And for a NAND, 0 is a controlling value, NOR is a 1 is a controlling value. So these are the controlling and inversion values for the basic gates. Now here, for every gate, we will check whether it is a controlling value. Any one of the input is a controlling value, and how many if no controlling value, then whether it is a U or not. But in the input okay, so here in the flow chart we can see that if we obtain a next input, whether it is C, whether it is controlling value, then it is C XOR I. If it is not, then we will verify whether it is a U and we will make it true. And here, if it is a U, then we will return the unknown. If not, we will return C complement XOR I. So the next, in the input counting method, we will count the changes in the values. So like we will update a counter. Say now, if some gate switches from say 0 to U, and now if we consider this gate to be an NAND gate, so the control it is changed from 0 to U, so the count of the controlling gate input is decreased, whereas the count of an unknown has increased. So in this way, we will now see after updating these values, if the C count is not equal to 0, that means there is either any one of the non-control controlling value present. So the output should be the controlling value XORed with I. And if not, if this is not equal to 0, that means there is a presence of any unknown value. So the output should be unknown. If this is also, there is no unknown, if both become 0, then similarly C complement I. So in this way, the same previous method, but we update the list and then evaluate it. If there is no change, then the previous output will remain. So in this way, we keep a counter for the controlling and the unknown inputs. So the next is the parallel gate evaluation, where we can, like if we have a 32-bit computer, say, so this word size of a computer we can use for evaluation. So we can evaluate 32 logic operations in parallel. So if we say, for example, if we consider 4-bit and we are performing this 4-bit parallelly. That means 0 or 0 will give 0. 1 or 1 is called 1. Next, with this 2, we'll perform an AND operation. So it should be 1, 0, 0, 0. So at a time, we will get 4-bit output. So next we have a multi-valued logic. So if you have a ternary logic, for example, and if you consider that the word size is W bit, wide word, then the symbol encoding for representing 0, previously binary logic, so we used 0 and 1. So 1 bit was sufficient. But now we want to represent V1, V0 and a symbol for unknown. So the V0 we can encode as two zeros, 0, 0, 1, 1, and unknown is either 0 or 1. So these are the symbols for V0, V1 and VU. So now if we assume that, say, we will take some example. So if we have an OR operation, and how we will perform OR for this? If this is A1, B1, A1, A2, B1, B2, then we will perform the OR with 0, 1. So if we are performing OR between these two, say V0 or V1, then it will be 1, 1. Means we will perform A1, B1 OR operation and this OR operation with A2, B2. Similarly, but for an NOT operation, say we want to perform for an say U, which is 0, 1, it will give 1, 0, but we don't have any symbols for this. That's why for NOT operation, we will not perform like this. We will perform it inversion of this and inversion of this. So again, we obtain V. So this is about the multi-valued logic and having encoding with three different symbols for we are representing U also. So here we want three values. So we need 2 bits to represent and how we perform the different operations. Next, coming to the timing model, we have few types of timing models which we will see. The first one is the transport delay model, and next is the inertial delay, and third is the wire delay, and the fourth is the function element delay model. So with this, we will just briefly discuss about this delay model. Coming to the transport delay is the time duration it takes for the effect of the input gate changes to appear at the output. So if it is nominal delay of 2 nanosecond, this effect of the input change to be visible at the output takes 2 nanoseconds. That is the meaning of the transport delay. And this change at the input should take a nominal delay of 2 nanoseconds to be visible at the output. Now, if we have a rise and fall delay, so if we say 2 nanoseconds to rise, so this rise to affect to the output and output to rise will take 2 nanoseconds. And the fall is 1.5. So this fall from the input to be visible at the output will take 1.5 nanosecond. And a min-max delay means this change will take between 1 or 2 nanoseconds. So between this time, any time my signal can rise. And similarly, this fall can also take between 1 to 2. This can be either this or this or this. Anyway, here also it can go down. So it's between one or two. So any the transition can happen in this window or this window. So this is about the transport delay, which again we have seen in the nominal, rise and fall delay and min-max delay. So the next delay is the inertial delay, the minimum input pulse duration necessary for the output to switch. So this is the, if we say D1 is 1.5 nanosecond and Dn is 3 nanosecond. This pulse duration is just 1 nanosecond. So which is not sufficient to switch. So output we will see there is no switching. Whereas the duration now is longer than 1.5 nanosecond D1. So there should be a switching, and that switching should happen after Dn nanoseconds, which means this transition should be visible after 3 nanoseconds. And again, this should be visible after 3 nanoseconds. That is the inertial delay. Inertial delay is like we need some minimum delay for the input. Like this transition, it should be staying at logic high for a minimum duration for the output to also switch. For this transition to appear at the output, we need a minimum duration, which is in this example is 1.5 nanosecond. So the next is a wire delay. Wire delay depends on the frequency. So now if you are going for RF frequency, high frequencies, then this inductor effect will come. Otherwise, we will be able to see the RC effect, resistance and the capacitors effect. So wires are inherently resistive and capacitive. So it takes some time for the signal to propagate along the wire. So you could have seen there is an delay because of this R and C, because of charging of that capacitor. So if we consider this wire can have a delay of from A to B. So if you are having this much long wire and this much long wire, so it depends on the length of the wire and also the frequency in which it is operating. So we have different delays: D from A to D, D from A to C, D from A to B. So it takes a finite amount of time for a signal to propagate along the wire. And next is the function element delay model. For a more complicated functions, like if we have functional elements, if say we have some flip flop, if we consider this as a D flip flop, so there is a preset. So output should go to, because of the preset, output should go to high. So for this to go high and for this to go low, there can be a certain delay associated with it. And similarly, if we have a clear for an output to go low and Q bar to go high, we have a certain discharge and charging delays. So in the similar way, we have certain delay associated, and this is the functional element delay model where based on the functionality we are saying, okay, this is falling. To charge this node, we need this much time. This is a modeling for a delay for some complicated functional elements, such as example representing flip-flop. So now we want to simulate the circuit. So to simulate, if we, this is our for fault-free circuit. So if we consider a compiled code simulation, so it translates the uh, logic network into a series of machine instructions. So any logic network, we can convert it into a machine code with the gates and interconnects. So here you can see we are converting it to a code. So if we have the vector, we just read the input vector and run this compile code with the input vector, and we see the output. Again we check if there is a next vector. If not, we can complete the simulation. So the compile code flow, we perform the optimization of this logic and levelization, and then we said we want to generate a machine code, and then we perform the compile code simulation. To this too, we will see briefly. So to optimize for an any AND gate, if it is 1, it's a non-controlling value, so we can remove it. If we have only one input, which is connected to this, it's equivalent to a NOT gate. And this is a controlling value, so it's like output is always going to be 0. And if we have 3 inverters, which is equivalent to 1 inverter. And a buffer can be modeled as a line. So this is done for the simulation purpose, not at the circuit level. In a simulation, we see that, okay, if this is the case, then can I optimize it to this so that we can reduce in the simulation time. Next is that we levelize the circuit. So if say to simulate this, we need this value, this input value. So that means this gate has to be evaluated first before evaluating this gate. So that's why we levelize it as L1, L2, and then we will simulate it. So for this, if we see this example, if we consider A, B, and C are all 0, so first we have to connect it to G1 and G2. So we have to evaluate G2 and G1. This and this. Then we see that G1 can be evaluated, but not G2. So G2 we retain in the list, but now G1 is evaluated. So next stage G2 can be evaluated. But to evaluate G3 or G2, we can evaluate together. So this we can evaluate in the next stage. But to evaluate G4, we need both G2 and G3. So after completing this only, we will take the G4. So G4 comes to the level 3. This comes to the level 2, and this is level 1. So we can see G1 is in level 1, level 2, G3 is also in level 2, and G4 is in level 3. So this way we levelize the circuit. So the code generation is like a high level programming language source code. So the high level language, the advantage is that the high level programming language, the advantage is that it's easier to debug, and it can be ported to any target device because it's not specific to the machine. We are not writing the machine code. So it can be used in any other target machine also. But we need this compiler. But there is a limitation with the compiler also. That is the compilation time. So with this we have some limitation in the application. But whereas if we have in the machine code itself, so if we can write the generator code in the machine code itself, it is highly efficient. The simulation time is efficient, the higher simulation efficiency. But if we can't change like port to the other machine because it's directly on the machine code, so it's not as portable. And also its simulation is like higher simulation efficiency. The other type is the interpreted code. So the target machine is a software emulator, and the code we interpret like execute one line at a time, like one and at a time. And this offers both portability and maintainability. We have seen the compile code simulation. Now in the event based simulation, wherever the event occurs, those portion alone we will simulate. So like this input is changed. So we need to simulate this gate. Now here the event has occurred, so we have to evaluate this gate. And if once we evaluate it, it's having no change, so we can, like, this portion need not be re-evaluated. So we can just keep this j equal to 0 as before. But this portion has changed, so we have to evaluate this and also this. So event driven simulation, like the switching of the signal value, is called as the event. So an event driven simulator monitors the occurrence of an event, and it will determine, like, with this event which gates we should evaluate. So if we consider a zero delay based event, so every gate, it's a combinational portion. Every gate we assume it's going to have a zero delay. So wherever we see, we read the initial condition and we come to the test inputs, and we see if there is an event, we put that events into the activity list, and we will be evaluating those. Once the list is empty, we will go to the next pattern. But if we want to add a delay to that, like some nominal delay, then to every, say for this we need to have a time scale. Again, to evaluate, we have some different time scales. So if we see this with an example, so we need to have the two pass event driven simulator. Like, we need to maintain the schedule along according to the time. So now if we consider that G1 is having 8 nanosecond delay, G2 is also having 8, this is having 4 nanosecond, and this is having 6 nanosecond. Now we see that it's 1 0 0. So we know that we have to evaluate G1, G2 because of A1, and because of C and B we have to evaluate G1, which is, we, like, start with it. And now if A is changed to 0, so with this initial values, if we evaluate, it's like 0 0 0, and get output is 0. This is 1. So now for this, if A is changed to 0, we have to evaluate this H. Along with this, we have to schedule with the time. Once we schedule the event, we have to schedule with the time. We look at gate G2, which is going to give the output H, and the input is 1, and the time is 8. So H we are scheduling, input is 1 and 8. Similarly, we have to schedule for E, which is having a delay of 10. Again, so for this event driven example, so every time we have to schedule with the delay, which is the nominal delay. So this change, we said it should occur after 8 nanosecond delay. So you can see after 8 nanosecond delay, this change is reflected. So the similarly for the other changes. So what is the difference between the compiled code and the event driven is that the compiled code is a cycle based simulator. So it will have a high switching. It is useful for a high switching activity. So now if we take an event driven, we are maintaining the list of activity and scheduling the event. And once if there is too much of activity, we have to simulate the complete code. For that, we can go for a compiled code simulation itself. And we can also perform parallel simulation. The limitation is going to be the compilation time. But for an event driven, implementing gate delay and detecting hazards is useful. But it can be used for circuits with low switching activity. This is about this. Um, just write one or two points. The event driven can be used when the switching activity is high. And event driven, we need like low switching activity, but we can detect the hazards because we are able to model the nominal delays or the delays. So now we said hazards. So what is this hazard means? It's an unwanted transient pulse. Now if we consider this output is like its A is at let's see 1, this is 1 to 0, and this is 0. So this is 1 to 0, and it should be 1 to 0. This is 0 to 1 NOR gate. This is a NOR gate truth table. So it's 1 0 0 and 0 1. So both the values it should remain at 0. But because of some glitch or some delay, if this inverter adding delay is causing some output to transition remain at high for some duration of time. This is called as the glitch hazards. So in the hazards, again we have few types of hazards, which is the static hazard and the dynamic hazard. So static hazard refers to the transient or the pulse in a signal whose static value does not change. So it's like 0 one time going up and coming. But in a dynamic hazard, the pulse during 0 to 1 or 1 to 0, in the transition we see a hazard. Like this, it should remain always high, but there is a transition and it goes down. So it's called as static one hazard. And similarly, it should remain 0, but it goes up for a duration. It's called static 0 hazard. And dynamic, so there is a transition we said 0 to 1 or 1 to 0. In between, we see that it goes up, again goes down, and then goes up. So this is dynamic one hazard. And then similarly, this has to go down. Instead of this transition, it makes some transition, goes up again, then it comes to the ground potential. So this is the dynamic zero hazard. So to detect the static one hazard, we can have, if we have say one vector v1 and v2, we add a new vector which will be represented like this. So we detect this fault saying that if it is Vi if both the vectors are same. It means there is no hazard. If they are not equal, then it is an unknown value, so there is an hazard. So we deduct by V1 plus V2, which can be like any signal which is 0U0 or 1U1. Somewhere in between it's changing. So there is a possibility of static hazard. Now what is the before going to fault simulation, multi-valued logic. If we have six valued logic, the static 0, it should be always 0, static 1, it should be always 1. Now in the rise transition means it should go from 0 to 1 or 1, 0 0 to 1 or 0 to 1 1. And so it's like this portion, if we take, it can be either 0 or 1, so we can represent as 0U1. And similarly for the falling. Now in the hazards, we can say we have said 0U0 or 1U1 is for the static 0 and 1 hazard. And to represent the dynamic hazards, we need to use the 8 valued logic, where you can see this was one of the hazard. So it's like 0 1 0 1. Then 0 1 0 1, which is the hazard for dynamic one hazard. Okay, so next is what is the fault simulation. So we have a circuit, we have a given test pattern and a test model or the fault model. Say, okay, this is a simulator. What and all we need to give is the input. We are given with a circuit, test pattern, and a fault model. So what is the fault model? Either the structured fault model or the bridging fault model, or it can be a delay fault model or any other higher fault model. And what we determine with through this fault simulation is that we get some output, we can determine whether it is a faulty output or a fault free output, whether the test pattern is able to detect that fault. And next, so when a test pattern is not able to detect the fault, we have undetected faults. So if we have a set of how many faults is detected by the test pattern, how many faults are not detected by the test pattern, we will get a metric called as fault coverage, a score. Say 99% of the faults are getting detected by this set of test pattern. So these are the output we can obtain from this fault. Like we can determine if we perform a fault simulation, and to perform a fault simulation, these are the things which is required. Now, what is the time complexity of this fault simulation? If we consider that n is the number of logic gates and p is the number of test pattern, so how much time it takes if f is the frequency of the number of model faults, uh, model fault, these two are approximately roughly proportional. So if we have say two gates, the model fault will be proportional to the two gates. So we can write the complexity as order of p n squared. So this is the time complexity for a fault simulation. Now we will see some methods of performing the fault simulation. So we have seen the true value simulation. Now we are going to see the fault simulation. Before this, any doubts? Okay. So if no doubts, we'll just proceed. Serial fault simulation, as you see the word serial, we will just perform first the fault-free logic simulation. So we will have some good fault response, that is the golden response. Next, we perform the simulation by injecting one fault and then performing the logic simulation and then getting the response. And that response is the faulty response. So you can see we perform the fault-free simulation. Then we inject a fault and we take the pattern and then we get the simulation like done, and we can compare with the golden response whether there is a mismatch. If yes, that detects this particular fault, this pattern detects this particular fault. If not, it is not detecting, we will go for the next pattern and see whether it detects a fault. So this way we perform serially. So now if we take the pattern, this is the input pattern 0 1 0, and we can see that the output is 0 but the good output is 1. So if we represent fault free upon faulty, it is 1 upon 0. That means we have detected this. This pattern is able to detect the fault F. And now if we apply the second pattern, this execution is completed. So next we move on to the next pattern. And we see that this good response we have simulated and stored it first, initially in the first step. Next we got the output 0. So again we can say this is detecting F. But what about G? We inject this fault and perform the simulation and see that both the outputs are same as the fault free. So this is not detecting this fault. Whereas P3 when we apply, we can see it is giving 1. That means it is able to detect G. So let's try just, so we can say that either P1 or P2 or P3 and P3. P1 or P2 and P3 is required to test the fault F and G. So if we consider F fault is there, now this 0 will excite this fault. And what is the value here? 1. So 1 0, fault free is 0, faulty is 1. This is going to be 0. So for 0 0, it will remain 1, and this it will remain 0. So we can see this fault is getting detected. So next we will go for the fault dropping. So if, for example, suppose we are simulating P1, P2, P3 in an order, and if F is detected by P1, so we need not simulate the fault F for P2 and P3. So we can drop the fault F and then proceed. So this is called fault dropping. But this we cannot do if we are performing the fault diagnosis. For the fault diagnosis, okay, let's just do it. If we have P1, P2, P3 are the patterns and we are simulating in this order. If P1 is detecting F, we can, the fault list is F and G. Now we can drop this fault F as it is already detected and a new fault list will be G. So for simulating P2 and P3, we can do it on list G. But this we will be we will avoid this fault dropping when we want to perform the fault diagnosis. Fault diagnosis means which portion is causing the fault or that error. So that time we need to perform like we will avoid this fault dropping and we will perform entire fault simulation. The advantage of this is that it is easy to implement. The fault dropping and not the fault dropping, this method. And the disadvantage is that it takes time, so it's very slow. The serial simulation. And it can handle like wide range of faults, so it can like it can be used for the fault. So next one, now we have done the simulation in a serial way, like one fault at a time. First the golden or like fault free, next one fault at a time. So now in the parallel fault simulation, what we will do is that we can simulate it parallelly. So in the parallel simulation, we have two types, which is the parallel fault simulation and the next is the parallel pattern fault simulation. We will keep the faults in parallel and simulate, and next we will keep the patterns in parallel and then simulate. So in a parallel fault simulation, we are going to keep one fault, one bit. So one for the binary logic, one bit of information is sufficient. So if we have a W bit word, we can perform the W parallel simulation in which one will be the fault free and we will have W minus 1 faulty circuit. So we can perform both the faulty and fault free circuit in parallel and using the bitwise operator, like bit by bit, this bit separately, this bit separately. So using the bitwise operator. So if we consider this, then we can say that to inject a stuck at 1, we need to add an OR gate. So if we add an OR gate and apply a 1 to this node is going to be 1. So now this portion, this is for fault free. This portion we are trying F stuck at 1. And similarly, we want this node to be stuck at 0. So we inject an AND gate. Now when we apply a 0 here, this is going to be always 0. That means this is going to perform the, and 0 here is a non-controlling value. This is going to perform the operation for G stuck at 0. And this is not going to affect the G stuck at 0 operation. So this is how we will modify the circuit and we will have parallel. So we can see if we have 3-bit word, this is for fault free, F stuck at 1 and G stuck at 0. This one is non-controlling for an AND gate. So this will not affect the F simulation. So here you can see that we are simulating this 3 in parallel, F for fault free, F and G. For pattern 1, next again we will apply the next pattern and the similar. But if we go for the next method, which is the parallel pattern fault simulation, we will see that we will keep the patterns parallelly. First we have the fault free and we simulate for 3 patterns. Next for F faulty, 3 patterns. Again G faulty, 3 patterns. So in this way we will keep the patterns in parallel. So the next method is the deductive fault simulation. Before that, just to read few points on the advantage and disadvantage of this method, which is a parallel fault simulation. A large number of faults are detected by each pattern when simulating the beginning of the sequence, and the disadvantage is unit delay model is only applicable because we are performing in parallel, so we are not accounting for any other delay model. And faults cannot be dropped unless, see, once we have the faults in parallel, we can't drop this fault once P1 is detected. We have to complete this complete word, and in this word, if we drop also, this is going to be evaluated. Like this bit position is going to be used. So we cannot drop the faults unless this all this W F is directed, G is directed, then we can drop and change to the next fault. Okay. And the parallel pattern simulation patterns we have seen, we are keeping parallel. So if we have a W with data, W test patterns are packed and then simulated. So first the fault free, then next the faulty. So single fault, first fault free simulation, next for each fault, fault injection, and then fault circuit simulation. So here the advantage is that if a fault is detected, we can drop the fault because we are simulating patterns parallelly. And best for simulating test patterns that come later when fault dropping rate per pattern is lower. And this is not suitable for sequential circuits. So the next method we go for is the deductive fault simulation. Our idea is in these simulations is that how to reduce the simulation time. So this formulas, I think we can go with an example. Now, if we consider the pattern is 0, 1, 0, what are the faults it can detect? A stuck at 1, opposite value, and then B stuck at 0, and C stuck at 0. So with this, we get an output of 1, which can deduct E stuck at 0. And what are the faults that we can propagate? A 1 to an OR gate is a controlling value. So only this fault we can propagate it. So only B stuck at, not stuck at 1, stuck at 0. B stuck at 0 can be propagated, and this fault will be masked. Now whatever value of this, if it is going to be fault free one, then it is masked. These are the two faults we will be able to propagate. Now let's come to this portion. It is 1. So this can detect L stuck at 0 added. This is a controlling value. So now only this fault can be propagated. This will be masked. Next H, which is 0, so H stuck at 0, stuck at 1. Next, this is a non-controlling value. So both these faults we can obtain at the output. So it should be the union, like both A, H and B, E, F and J. So these are the faults which will be detected by this pattern 0, 1, 0. So this deductive fault simulation is something like based on some logical reasoning rather than simulation. We are saying that okay, this is 0, so this can be detected. Okay, this is a controlling value, only this fault can be propagated, non-controlling fault will be masked. So the fault list attached with the signal X is denoted as the L into LA, and for everything we derive a set of fault list, and based on the logical reasoning we propagate the fault. So this is very efficient to simulate, like we can get so this much fault in just one pass, but this is not easy to handle if we have an unknown here, then we can't say which are the faults. reason which are the faults are going to be detected. And this can be useful only for a zero delay model. But there is a memory management problem also because we have to handle this list also. So now example 2, we can see if we have a 0 here, we have changed this to gate inputs. So this is now detecting B stuck at 1 and this is detecting C stuck at 0. This is a non-controlling value and this is a controlling value. So now this fault will be detectable. And next this is coming here. So similarly we can see 0 0, we can detect this fault. The other faults because of A, which already like detected by the previous pattern. And similarly for A1, we can detect this fault. So we have this list. Now we can see there is a controlling value. So this controlling value only will be appearing here. Like we will be without mask. These two are going to be masked. So this two will be masked, not this two. E is also here. This three will be masked. Even this will be masked, but because of that, this three will be masked. So only this two will be propagated along with this K. So any doubt in this deductive fault simulation? So is this deductive fault simulation clear to everyone? This deductive fault simulation. So the pattern is A is equal to 0. So what will be the fault that 0 can detect an opposite value? So A stuck at 1 can be detected. So we maintain a list for that this particular net. So we got this list. Next, similarly for the B, we have a list of 1 is applied, so stuck at 0 can be detected. And here is a 0. So we have stuck at 0, opposite value can be detected. So stuck at 1 can be detected. So this is the first stage. Now next stage, first we have to evaluate G1. For G1, this 1 is a controlling value. Now if we consider 1 and whatever the fault here, output is going to be 1. So this fault will remain undetected. So this can be propagated. This will be propagated. And next E is 1. So stuck at 0 at E can be detected. So we got the list at this node. Now we come to the L and F. They are fan out branches. So again L is 1. So L stuck at 0, F stuck at 0. We got two faults. Now this is a inverter. So directly B, F and E can be detected. For inverter, it's just a single input. And this is 0. So stuck at 1 at this J line can be detected. Next, we are here to this G2 gate, and this is a 0, which is a controlling value at A. That means whatever the fault is here will be masked. So this is going to be masked. That means we are able to propagate A1, stuck at 1. And this line is 0, so it is going to be in stuck at 1, can be detected. Now this pattern can detect because both are non-controlling values. So both these faults can be propagated to the output. So this was the first example. In this example, when this part was having a controlling and non-controlling value, these are the list of faults which can be detected by the controlling portion also. We previously said that controlling portion will propagate. But this is also present in a non-controlling, which will be masked here anyway. So this will be masked. Only this two will be propagated to the output. So from this concurrent simulation, in a one go, we have a pattern 100. So it can detect 3 faults. Previously, if we want to do a serial fault simulation, we need one golden simulation. Next, we could have taken this pattern and simulated across this 3 fault, complete fault list, and then we could have identified that these 3 faults are going to be detected by this pattern. But this simulation, in one simulation, we got to identify that, okay, this is the pattern, these 3 faults can be detected. This is the deductive fault simulation. Is it clear now? Any other doubts? So I'm going to the next type of the simulation, which is the concurrent fault simulation. Uh, Till now, whatever the logic and fault simulation part, is it fine, right? Any doubts? If no doubts, then we will see one example for the concurrent fault simulation. So we will see with an example itself. Now, if we are simulating, say 1 at line A and B. So let's consider this as the circuit. Now, if we have 1, what will be the output? It will be 1, and this will be 0, and this will be 1. So, what are the equivalent like simulation which can be performed concurrently? This is a good value 1 0 and 1 0 1. So, what are the next set of patterns for this AND gate we can perform? We can consider that A is stuck at 0 because pattern is 1. If we perform that simulation, the output will be 0. We can also perform B stuck at 0 because again the pattern is 1 and this can be 1. And also we can perform C stuck at 0 simulation because the output C here is also 1. So this is going to be 0, output is 0. The third simulation which is also possible is E stuck at 0 because E is 1. So this is 1, this is 0. But what is the input? Both 0. Similarly, for this inverter, what are the concurrent simulation which are possible from this pattern is we can have B stuck at 0. So it is 0, 1. And similarly for D also it should be stuck at 0. So 0, 1. And now F, it should be 1 because output is 0. So 1, 1. So for this gate, again, what are the concurrent simulations we have? We can say that A is stuck at 0, then what will be the output? Similarly, B is stuck at 0, then what will be the output? C is stuck at 0, what will be the output? E is stuck at 0, G is stuck at 0, F stuck at 1, and D stuck at 0. So we can see that in this is not detecting the fault, this fault is also not detected, this is also not detected. And we are able to detect the fault with this test pattern. And now the advantage of this is next, if this is changing to this 0, only this gate is sufficient to be re-evaluated and of course this good value. And similarly this. So the other gates in this list can remain unaffected. So we can use this B0, C0 and E0. In this way we can get that efficiency. So this is about the concurrent fault simulation. Next, let's just take an example and solve for the deductive fault simulation. This is A, B, C, F, E, G. Okay. With this 1, 1, if you can even turn on your mics and answer. So what will be the possible simulation for this particular net? The LA, if you want to say. What will be the fault list it can simulate? If you have any doubts or if you have any answers, you can also turn on your mic. So for this particular A equal to 1, what will be the fault it can detect at that net A at this point of time? Because of 1, it can detect an opposite value which is A stuck at 0 if I represent this notation. For this, it can detect B stuck at 0. At C, both B and C can be detected. And here, both D. Now, this is 0. That means B0, D0, F1 can be detected. At this node, both are 1, 1, which are non-controlling. So, we will get a union of both. That means A0, B0, C0, E0. Because E is also 0 here. Not 0. E is going to be 1. So, stuck at 0 can be detected. Now, this output is 1. Now, for an OR gate, this is a controlling value. So, B is in the this list. So B cannot be detected. B will be masked here, so it will be masked here. That means A C0 E0 will be propagated, and also this gate stuck at 0. So if we want to write in terms of the expression, it's like LG is equal to LE intersection union G0, and here it was like LE. So I have just given one example for deductive for simulation. Next we will go for some problems from the previous year assignments. For a certain delay model, it is required to have a minimum duration of input pulse to register the switching at the output, identify the delay model. So we have already said that inertial delay, there should be some amount of time for the transition. Like this transition, it should be for 2 if the D1 was 1.5. We saw that if it is 2, then this transition is getting like propagated to the output, and this is propagated with the DN delay. So it's an inertial delay. Next question, how many entries a truth table will have for a multi-valued logic evaluation, provided that we are using 5 symbol logic system and 4 input logic in input? And can you answer this? Any answers? What is M? It's log 2k. Sorry, this is. What is k? What is the value of k? So if we take M is equal to say k is 5 symbols. So log 2k, and we have to take the upper limit. So this is 3. And what is the n? 4. So what is the formula? 2 to the power n into m, which is 2 to the power 4 into 3, which is. Next question, a logic gate is driven by 4 logic gates PQRS, which are assigned with the logic levels respectively. Determine the logic level of gate G. So there is a gate G which is driven by some set of gates which maximum depth is 30 level is 36 on depth, sorry. The level is 36, which maximum level is 36. Then the level of this will be plus 1. So the answer is 37. Is this clear? So we will go to the next question. Identify the incorrect statement about the code generation. So we said the code generation, we can use high level machine code and interpreters. Interpreters are also portable and are more portable than the high level language, and we do line by line. And high level programming language are easier to debug and also easily ported to other machines. Machine codes are efficient, higher simulation efficiency we saw. So they have given it is less efficient. So this is the correct answer, which is the incorrect option. So again, which are the incorrect option? Compile codes are used on high switching activity circuits, whereas event codes are used for low switching activity, because events we are evaluating, we are maintaining the activity, scheduling that, and if there are more switching, then we have to evaluate more number of events. So for that, compile code will be advantageous. Compile code can detect hazards while event driven code can't. So this we said compile codes can't detect hazards, because we are writing it as a code and we are not modeling any delay. And compile codes are cycle based simulator. Yes, we are doing it, levelizing it, so it's performing cycle by cycle. So the option which is incorrect is the compile codes can detect hazards. So next is identify the following 6 valued logic hazards in the given order. So I think this question we have already seen. Can you answer? It's like 110. So we can see it's a falling transition. So we have both sides. Next is 101. What is this hazard? And the other hazard is this 010. And next is 011. So this is rising transition. So what is this hazard called as? A is static one, means it should remain always 1, but because momentarily it goes to 0. So this is called static 1 hazard and this is called static 0 hazard. So static 1, static 0. So it's option D. So next question. So what is the fault dropping? Fault dropping, we said that if a pattern is able to detect a particular fault, then we will drop that fault and we will proceed for the next pattern. So it's like eliminating, stopping the simulation for a fault as soon as it gets detected. We are not eliminating any faults with respect to any significance, or we are fault dropping is not about equivalence, and it's not about this coverage. It's about once detected, we will eliminate that from the fault list. So next question, select the correct statement regarding the fault simulation. So parallel fault tries to detect multiple patterns faults for same pattern, and this is multiple patterns. And if we have parallel fault simulation, we can model with only zero or unit delay, not for the nominal delays. So all of this. Okay, this question. The following gate fault list propagation determine the fault set of the node M for the following AND gate. Can you answer this? I think we have solved almost some 3-4 questions. If these are the list coming from some because of some other logic circuit connected to it. Can you tell what is the controlling value for an AND gate? Or what is controlling and non-controlling value? So what is the controlling value for an AND gate? So 0 is a controlling value for an AND gate, and why we call 0 as a controlling value? Whatever will be the input at this node, the output is always going to be 0. So now here H is in the applied with the controlling value. So the fault which can be directed at M. So first is that M, it is in 0, so stuck at 1 will be detected. The other faults, can A be detected? So the faults A, B and C, A stuck at 0, B stuck at 1, C stuck at 0 will be masked because of having a controlling value at this other input. So that means only this false, if it does not appear in this set, can be propagated. Yes, F is not present there, F can be propagated. H is also not present, so can be propagated. So this will be the fault list. So we have seen A, B and C will be masked. So because of H0. So the faults that can be obtained is F stuck at 1, H stuck at 0 and M stuck at 1. So next question. Among the detecting fault simulation, differential fault simulation and concurrent fault simulation, ranging them in increasing order of the respective speed. Actually, the differential simulation, if you see, it combines the concurrent and parallel pattern based simulation. That means it is more like faster than compared to the concurrent. So increasing order of the simulation time. So deductive will take the lesser number of time, followed by concurrent. Sorry, not deductive, differential. And deductive will take less number of time because with logical reasoning, one simulation, we are able to identify more number of faults in a second. So actually the idea is in the differential simulation is to simulate in turn like every faulty circuit and track only the differences between the faulty circuit and the last simulated one and inject the differences as an event. So we can use something similar to an event driven simulation. So the deductive we are doing with logical, so it takes the very less number of time. Concurrent in one simulation we are able to see that like these are the circuits we have and differential we are merging it with the another parallel simulation, so it takes little more time. This is the order. Now parallel, differential and concurrent. So it takes less time. As you said, concurrent takes more time and the improvement of concurrent is the differential. Parallelly we are simulating, so parallel takes less time. So the answer is C. This one I am little having doubt. Why? Actually, speed and this is what? Okay, memory requirement. Okay. Speed wise, concurrent performs faster compared to the differential. And concurrent, you need memory for having for all the possible for that pattern gate simulation, that multi gate simulation. So it requires more memory compared to the differential. So the answer is C. This both the questions are with respect to speed and the other is with respect to the memory requirement. So any doubts? Otherwise, we will solve one example for event-driven simulation. Maybe. So okay. So now we will take one example on an for an event-driven simulation algorithm. So if we consider this logic state, A, C, B. Now if we consider A equal to 1, C is equal to 1, B equal to 1. The first simulation, let's just consider some delay values for this circuits. So this will be 1 after 2 nanosecond delay and this will be D equal to 0 after 2 nanosecond. This is I represented F will be 0 and 1 is 0 after 4 nanosecond and G will be 1 after 2 nanosecond. So now this is the initial Now, if we have an event at C, which is changing from 1 to 0, so let's just, okay, I can write it here. We need a time scale because we have some delay associated with it, each gate. And then we need to have a scheduled event and then the activity list. So at the time t equal to 0, we saw that the C is changed to 0. This will trigger the event for D and E. Values D and E will change. Now, at, at least 2 seconds t should wait. So t equal to 2, the event will happen. Both D and E. So D will be now 1 because this is 0. So this should be changed to 1. And E, which is 1 0. So it should also change to 0. So both the values have changed. Now this will change this value G and this will change the F. Now 3 again we have to wait either 4 or 2 or so 4, this will be 0. So here G will be 0. Next 5, 6. Now we have waited for 4 seconds. So this F will be evaluated. F is 1 now. Because of this changing to 1, again G has to be evaluated. So now again for evaluating G, 2 units delay has to be waited. Now G will be 1. So this is the event driven simulation. So like G went to 1 for 0 for momentarily and then came back. So this can capture this type of event hazards. We can model delay so. Uh, think is this like fault simulation clear for everyone? So we have discussed some few types of fault simulation briefly: event driven, concurrent, deductive fault simulation, as well as parallel and parallel two types. So any doubts, or maybe we will discuss some type of faults. Uh, okay, some newer type of fault. Just I thought let's discuss some other testing method such as IDDQ based testing. So if we consider a CMOS circuit, say an inverter, this was like we previously said that we can detect some fault, like if this is always on. So it's like stuck on fault. So it's like whenever we are switching, we see some at the switching time, some current is drawn. But when there is a stuck on fault, so there is a direct path from VLSI to ground, and we observe that this IDDQ current remains high. It's IDDQ, not F. This current drawn remains high. So once we have some probe and we measure it, we can detect certain like stuck on faults by measuring this current. And there are other testing methods where we say very low voltage testing, where we reduce this VDD voltage by 2 to 3 times of the threshold voltage to detect certain. So this detects few other faults. So these are like fault testing methods. And also we have testing with varying the temperatures, like low voltage or stress test, like stressing it at different temperatures and testing. And for the scan flip-flop, we have already discussed that we use some flash patterns to test it. So this were like some, and for whenever we have a sequential element, we use sequential ATPG to generate some patterns and test. And for combinational, it was like combinational ATPG. So this was like some testing methods. So it's like we perform the fault simulation and know which patterns are detecting which faults. We generate those patterns by using an algorithmic method such as automatic test pattern generation. And for applying such patterns at the structural testing, we use an instrument like called as automatic test equipments. So just I thought briefing about the testing. So any doubts? So if no doubts, I will end this recording. Thank you all.